Right. Good morning, everyone. It's my pleasure to introduce our first speaker this morning, Professor Christophe Grojean from DESI, the CERN group in DESI. Professor Grojean works on various topics in particle physics beyond the standard model. He's especially specialist in the physics and dynamics of the Higgs bosons. He also works with experimentalists to establish the profile of this new type of particle. But today, his topic is more related to the this collider devices, because he's also involved in various groups working physics case about the next generation colliders after the LHC. So let's welcome our speaker this morning.
Okay.
Yep.
Good. Thanks a lot. Good morning, and thanks for the invitation. It's certainly always nice to be in China. And today I would like indeed to tell you a little bit more about this next big project at CERN that will come after LHC, which is the Future Circular Collider. And as you know, there is also a very similar project in China called CEPC. The physics case is actually very similar. So yeah, we'll be discussing the CERN, but you could also take it for the Chinese project. So, let's see. So what is FCC, right? The Future Circular Collider. So it's a versatile particle collider housed in a 91-kilometer underground, about 200 meter underground on average. And it will be implemented in several stages. First, it will be an E+, E- Higgs electric flavor top and QCD factory running between 90 and 365 GeV. And that's exactly what we call FCC-ee. And then, like what you did from going from lab to LHC, you will replace the electron and the positron by some proton to reach energy maybe of 80 TeV, 100 or 120 TeV, depending a little bit of the magnet that are being developed at the moment. So this is FCC-ee. So what I want to tell you today is actually why do we need a new collider? So you already had several talks yesterday, by Tauran or John Ellis that motivate really a new collider, but I will say a few more words. And then I will report about the FCC feasibility study, that started a couple of years ago at CERN, and that will be ending in March next year, just to establish whether this collider is something that is feasible or not. And then I will review really the physics program of FCC-ee. I will also tell you that the integrated program EE and HH really brings a new information about the Higgs and electric sector. And I want to insist on the fact that FCC-ee will actually be the best flavor factory ever. Right? And then I will comment on the broadest exploration potential of FCC-HH. So why do we need a new collider? I think we need a new collider simply because LHC has been very successful. He has established that the standard model is really a right description of nature up to very high accuracy, up to energy of several of TeV. And that was not a given outcome of the LHC. LHC has been really functioning very well, delivering a very precise measurement thanks to a firm control of experimental and theoretical systematic uncertainty. The Higgs boson has been discovered at a mass that was predicted by the lab electric precision data. And at the same time, LHC hasn't found anything else. And I think that's already a big discovery, not finding anything, bring valuable information about what do we expect, what is really the landscape of physics in the TeV scale. So traditional new physics models are certainly in trouble. And at the same time, there have been new approaches like the relaxion, naturalness, or clockwork, etc., that bring a new perspective on the physics above the TeV scale. So what does it mean? First of all, that the traditional model are in trouble. It means that the TeV scale naturalness agent, the guy that were needed basically to explain why the weak scale, why the X mass is not of the order of the Planck scale, those agents might not explain also at the same time dark matter baryogenesis. 20 years ago, people were sure that they will be discover supersymmetric particle, and the lightest of them will be the dark matter, and then you have enough source of CP violation, etc., to generate electric baryogenesis. So maybe, those different problems are decoupled from each other, and you really need to think differently. And all those new models, that have been designed lately also tell you that cosmology actually might have something to do with determining the vacuum of the standard model itself. So it's a new approach, you have to maybe to give up about introducing a new particle, new symmetry, but simply using the time evolution of cosmology. And, the thing is that the signature of those type of models are totally different. You don't necessarily expect new degrees of freedom at the TV scale. Rather, they will be light and very weakly coupled degrees of freedom. So certainly you need also a machine that can, probe the different energy scale and different couplings, right? So that's why we need a broad, versatile, and ambitious program that at the same time will sharpen our knowledge of already discovered physics. You want certainly to measure with high accuracy all what you know, to write the next textbook, basically. But you also want to push the frontier of the unknown at high and also at low scales. And together, FCC-ee and FCC-hh combine actually these two aspects. They provide more precision and more energy to really gain more sensitivity to new physics. So I want to insist on the fact that precision is a discovery tool. And there have been many historical examples from that. I mean, looking, for instance, with high precision of the Uranus anomalous trajectory led people to discover Neptune, right? So you discover basically a new particle or a new planet simply by measuring with high accuracy the particle or the planet that you already know. But sometimes, this precision measurement also bring new understanding of the fundamental laws of physics. I mean, that was the case of Mercury, again, by looking with high accuracy, the perihelion of Mercury basically led people to understand that at the end of the day, you need to give up of Newtonian mechanics and go to general relativity. There are also examples you can think about, maybe closer to particle physics. You can argue maybe that by looking with high accuracy as the interaction of the Z or W gauge boson to quarks and the lepton basically predicted the Higgs boson. So sometimes it's true that these discoveries were expected based on theoretical argument. I mean, that's maybe the case of the Higgs boson, that where without the Higgs boson, there is a breakdown of perturbative unitarity. You could also argue that quantum mechanics, in a sense, follow from some inconsistency of the Rayleigh Jeans UV catastrophe, right? But in any case, I mean, it's always true that precision gave valuable additional information. And in any case, experimentalists shouldn't lean too heavily on theorist priors or prejudice. You can remember certainly the discovery of parity violation. I mean, nobody except maybe Lee and Young were expected that parity will be violated. And then, there have been an experiment, and this experiment revealed that parity is maximally violated actually in the weak interactions. If you are able to perform, precision measurement, you should always do it anyway. You might learn something really important that is not expected. And I want to argue also that it's a time when you don't have a precise theoretical guidance, that's at the moment there is no really preferred model of new physics, that we really need powerful experimental tools to actually make progress. So the FCC project really offers an unprecedented opportunities on many different fronts. So it's true that there is no LHC or SEC-like no-lose theorem, but there is a promise to make a significant step forward in our understanding of the fundamental laws of nature. And you have to remember always that, it's not because you're not going to discover particle that you're not making progress. There is many examples in the past, where basically null experiment actually provide valuable information. Maybe the discovery of special relativity is certainly one good example. So there is certainly one sector, that requires more precision, is the X sector. So it's true that the X isn't everything, but actually it's the only thing. I mean, to paraphrase what Michael Peskin said, using some famous quote from a UCLA football coach, right? So the scalar discovery in 2012 has been an important milestone for high energy physics. Many of us are still excited about it, and I think everybody else should also be excited about the Higgs boson. First of all, because it brings new forces of different natures and the interaction that we know so far. There is no underlying local symmetry, there is no quantized charges, and those forces are also deeply connected to the space-time vacuum structure. And the discovery of the Higgs boson also opened new deep question. What is the origin of the Higgs boson? Is it an elementary and isolated, or does it emerge from a deeper underlying dynamics? Which role did the Higgs play during the Big Bang, and how did it influence the evolution of the universe? Does the Higgs boson play a role in explaining all the fundamental open questions in particle physics, which the standard model cannot address? I mean, flavor, dark matter, biogenesis, inflation, etc. There are always some model, where the Higgs is a key player really in all these problems. But for me, what is really important is actually that the knowledge of the value of the Higgs boson is actually essential to understand the deep structure of matter and the universe, right? So take, for instance, the mass of the W and the Z, right? Which at the end of the day controls the lifetime of stars. By the way, this lifetime of stars is also very similar, to the typical for life to emerge, to evolve, right? So this is a fact now that has been established at the LHC, that those masses are actually coming from the Higgs interaction. Coupling are deeply connected to the mass of the W and the Z. So this is a clear established fact. But there is other things, that we don't have any experimental evidence for. Right? So there are some theoretical models. Indeed, I mean, the standard Higgs interaction are responsible for all the masses of the quarks and the lepton. This is just a model that need to be verified experimentally. And again, we might have big surprises, right? And that's important, right? Because the mass of the electron at the end of the day sets the size of the atom. So the size of all the objects, the size of the universe, basically. And we want to know whether this has anything to do with Higgs coupling or not. So that's why we want to measure the electron, the Yukawa interaction of the electron. Yes. 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 Yeah, but I mean, you try, but I mean, the fact that, the sun is burning for whatever billion of years is related to. You will still get billion of years. I mean, switch off the mass of the W and the Z. Right? Go to the extreme when there is no mass of the W and the Z. What will be the lifetime of the stars? The weakless. I mean, if there is no mass scale, I mean, then where do you get the mass? Where do you get the time scale from? I mean, if there is no, but how the, and then they will decay immediately. They will burn immediately. I mean, okay, we can discuss that. We can solve the star burning. You did it, okay. Okay. Yes, I mean, coming back to the mass of the up and the down. So it's true that the Higgs has nothing to do, with the mass of matter as we know. I mean, the mass of matter we know is mostly QCD. Nonetheless, if you want to explain why matter is stable, you need to generate a different mass for the up and the down, because, QCD is isospin invariant, so it will give the same mass for the proton and the neutron. Now there is electromagnetism, that distinguishes the proton and the neutron, but electromagnetism, will make the proton actually heavier than the neutron. And this only because, the mass of the down is actually heavier than the mass of the up, in a sense, maybe fine-tuned way, that the proton becomes lighter than the neutron, and then matter can be stable, and also nucleon can be stable inside nuclei, right? So we want to understand whether this understanding that gives rise to the mass of the up and the down has anything to do with the Higgs interaction or not. So that's certainly something that the LHC won't be able to achieve, and you need a new collider to hope to learn and maybe verify or falsify the standard model picture. Then there is, of course, the question of what happened, a nanosecond or tenth of a nanosecond after the Big Bang, when this electric symmetry breaking occurred, and that is deeply connected, with the shape of the X potential, or maybe actually an extended X sector. If you want to have a first-order phase transition, is unlikely that you can achieve that only with a single X boson. You need to add extra degrees of freedom, and it's really the full understanding of this potential that can reconstruct the true dynamics. So if you want a picture really of the early moment of the universe after the Big Bang, something that you cannot do with telescope, because simply there is no light at that time, you need actually a collider to be able to understand these dynamics. And then there is a question of this imbalance between matter and antimatter, where you need new source of CP violation, and certainly the X sector is a good source of possible CP violations. So again, there are many open questions that you need to establish if you really want to have this clear picture of how matter come together, or it emerge from the Big Bang, right? And those questions, cannot be addressed at the LHE. So LHE and ILUMI LHE will make progress, but certainly won't be sensitive enough to answer those questions. So that's why we need a new collider to really make progress. So let me now quickly discuss and describe this feasibility study that started a couple of years ago. So that's really a result of the past European strategy for particle physics that ended up in 2020 and concluded that an electron-positron X factory is the highest priority for the next collider. For the longer term, maybe the European particle physics community has the ambition to operate a proton-proton collider at the highest available achievable energy, around 100 of TeV. But really, you need to start with electron and positron machine. So the CERN Council approved G, and the CERN management implements this. So that's why this feasibility study, started in 21, and it will be completed next year. And last fall, there actually been a midterm review to see if it makes sense to continue. So what was the objective of this feasibility study? Is first of all to demonstrate that you can really build this collider in the CERN area. That there is no environmental and administrative obstacle to really go forward. And then, you want to make sure that the whole state, France and Switzerland, agree that there is no strong opposition at least. And you want certainly to optimize the design of the collider and the injector chains. There is various, many constraints. There is the Lake Geneva, there is the Alps, there is the Jura. So is there a place actually to really put this collider on land, right? And then, you want to know exactly how much electricity you need, how much carbon you will produce, how much water will be needed. You will use to run this, to operate this collider. How broad you need to build to have access to this collider. All these things. Of course, you also want to make sure that you have the money, that you can secure the budget to build this machine and to operate this machine. And then finally, there is also always maybe a little bit of discussion about the physics, whether it's really worth building this machine from the physics point of view. So this layout. So this is a map, actually. As I say, there are many constraints. So there is a Jura somewhere here. There is the Lake Geneva, and if you go further in that direction, the Lake Geneva becomes very deep. So this means that you need to dig very much forward if you want to have the tunnel passing by. And then finally, there is the Alps over there. And of course, there are many cities around. So you need to really optimize to know where to put this collider. So there have been about 100 variants to the placement of this tunnel. And at the end of the day, things have been optimized, and we ended up with this particular layout. So this means that initially it was thought to be 100 kilometers. So now, if you take into account all the various constraints, the best scenario ended up with a 91-kilometer tunnel with 8 surface points with four experimental caverns, basically. Yes. Okay. And this is the state of the discussion that are going on with the various communes. So in green, this is a commune where discussion have been taking place with the mayors, with the various inhabitants of this place, and in yellow this is a place where discussion are going to take place next. So one important thing is to understand a little bit the structure of the rock where you want to build the tunnels. So this is more or less known. You really optimize the tunnel in order to avoid, for instance, any water, because when you're digging a tunnel, clearly entering water is a big problem. But you also want to make sure that the rock is stable enough, and to fine-tune a little bit the design of the tunnel. There have been some measurements that are going on in various areas in this around CERN. So if you walk around in the forest or whatever, or on the lake, you will find this machine that are just drilling, just to have a clear map of the rock where the tunnel will pass by. Now, an important question, of course, for all people that are living nearby is actually what are you going to do with excavated material? At the end of the day, something like 8 million of cubic meter, and certainly you don't want this excavated material in your garden. And there is basic principle is to reuse and minimize the disposal, right? So there have been some various ideas actually of how to reuse this excavated material, and there are some projects, for instance, that say that maybe you can add some fungi in this excavated material, and then you make this soil fertile that you can use for agriculture, for instance. It's also the question of what to do with the heat, that will be produced when you are operating the machine. So certainly there are some plans, to reuse this heat, for instance, for local houses and for hospital and schools. But there are also some cheese factories that are very much interested, because this machine will produce basically heat all year around. And, in the summer, usually, the houses don't need heat. But these cheese factories actually need heat, and it's very fortunate that certainly in the Jura and Haute-Savoie, there is really a need for this heat to produce more cheese. Then there is a question of, how to access the tunnel, And at the end, it was concluded that basically you need to build less than 4 kilometer departmental road to have access to the different point of the tunnel. So it's really minimize also the impact on the environment. Right? And there is a connection of how to connect this collider to the electric grid. Certainly, you don't want to have big disturbance on this electric grid, or you don't want the electricity switch off in Geneva when you turn on the machines and things like that. So this has been also discussion going on, with this electric company in France, and everything has been secured, and there is no major obstacle. You don't need to build a power plant near CERN, basically, to operate these machines. Now, of course, one big question is how to dig this tunnel. So this is really the layout of the rock, where the tunnel will be passing by. So somewhere here there is a Lake Geneva, so this tunnel will go under the lake, but close enough to Geneva in such a way that the lake is not deep enough, and you don't need to go to dig very deep, right? So as I say, on average, the tunnel will be 200 meters underground. For LHE is about 100 meters only, so it will be certainly more. It will be deeper. And the good thing, is that the structure of the rock is mostly molasse here. There is only a little piece of limestone, so limestone is not so convenient for the tunnel, so you really want it to minimize the place where you will go into the limestone. So at the end of the day, yes, so you will have this 8 access points, so there will be 4 experiments, so it's a 4 interaction point machines, and there will be other shafts basically to access the tunnel and to put the RF and RF cavities on all these things. Right? So there will be 2 large caverns and 2 small caverns. So the small caverns are basically of the size of the CMS cavern at the moment. Right? So you will have, the tunnel itself will be digged by tunnel boring machines. So there will be 8 of them going in the opposite direction on each of these access points. And they will progress at a rate of 18 meters per day. So basically, you need 8 years to really dig this tunnel. So by the way, this tunnel boring machine at the moment they are there is one company in China that can make them, right? So we'll need certainly a good cooperation between CERN and China if you want to exist on that. Yes, okay, let's move on. And this is a schedule, for this civil engineering. So clearly, there is many things that you cannot do in parallel. So you need to make sure that really you have a full control of what you can do. You start digging, and then you will install the magnet, etc. So it's a very complicated schedule. It's very tight also. As I say, you need 8 years. You will start digging in 2032, and you will be ending up in 2040 if everything is according to the plan. So yes, that's the thing. So this feasibility midterm report. So as I say, last October, last November, we have been asked to deliver a stage report. So it's a document of 700 pages. There are 7 chapters. One is about the placement scenario, the civil engineering, the implementation with the host state, the technical infrastructure, the FCC collider design and performance, the accelerator for FCC-ee. There is a cost and financial feasibility, which is a separate document because it's more confidential, it's more complicated, etc. So it's for different people also. So it doesn't really belong to the main document. And then there is a physics and experiment, which is about 100 pages. So of course, nobody is going to read this 700 pages document. So we have been asked also to produce an executive summary of 44 pages. And this has been reviewed by various committees, various bodies at CERN. So the Scientific Advisory Committee and the Cost Review Panel have been a meeting in October. Then the Scientific Policy Committee and the Financial Committee at CERN met in November. And finally, the CERN Council met in February. So clearly, each of these committees use a summary of the summary because, for the CERN Council people, reading even a 40-page document is too long. They want a 1-page summary. So that's a step, right? Every committee is basically producing a summary of the previous document. So this document is still confidential because it's work in progress, but it's available to all the CERN personnel. So if you have a CERN account, you can certainly access this document. So let me focus maybe on a physics experiment and detector. So as I say, it's about 100 pages. And these 100 pages really address the 3 different points, which is the documentation of the specificity of FCC-ee and FCC-hh physics case, the strategic plan for improved theoretical calculation, because it's not enough, to produce data. You need to make sure that you have all the available theoretical tools and theoretical calculation that are needed to exploit this data and draw some conclusion. And finally, you also want to understand what are the detectors that you will need to build in order to really achieve the precision or achieve, let's say, to control the systematic uncertainty at the level of the statistical uncertainty. So that's the structure of this physics chapter. So again, really reproduce these 3 main topics. So as I say, this document has been reviewed by various committees, and each of those committees really praise the work that has been done, the quality of the studies, etc. And what was maybe more remarkable is that even the financial committee underlines the need to make the project attractive from the physics point of view and takes the view that it would be unfortunate to really sacrifice the attractiveness of the physics for the sake of reducing cost. So they said, don't care about the money, we will make sure that we'll get the money to fund this project, but what is really important is that you understand the physics that you want to achieve. So even the CERN President Council say it's the first time I really hear, the financial committee saying such a thing. They always say, you need to cut the budget, you need to cut the budget. For the first time, they say, no, it doesn't matter, go ahead and try to understand what you want to achieve. And there have been various important people certainly visiting CERN. Picture of the French president with the Swiss president that came to CERN in November, and really it's important, for Europe to continue taking the leadership in this field, also, in view of the technological implications, clearly. And a little bit earlier this year, in April, even Fabiola Gianotti went to the White House to sign a statement of intent, saying that actually the US would like to join the project if CERN is going ahead and want to build it. So that was a big step forward, a clear commitment from the US, from the international community, clearly. So what is really the time scale, right? I mean, maybe one thing that you have to keep in mind is that actually we are only 20 years ahead from the first collision. So there is a lot of things that will take place in these 20 years, right? And I ask whatever computer and app that my kids like to play with to understand what it really means, 20 years, and that's the result, right? Nonetheless, yeah, there will be many things happening in those 20 years. So first of all, sometimes next year there will be this expression of interest from the community, trying to understand what kind of detector you want to install. There will be some conceptual design report that are expected in 2031, some technical design report in 2035, some installation of the machine in 2041. So just after the tunnel is completed, you want to install the magnet and etc., the accelerator, and finally there will be the commissioning happening in 2045 with the first collision. So fortunately, things are actually accelerating a little bit. The European strategy update that was planned for 2026, 2027 has been moved forward by 1 year. So, it's always good because you feel younger. Right? So that's the structure of the organization. There is various pillars in this feasibility study. So physics is only one little piece, clearly, but if you want to have this machine built and operating, you need to take care of accelerators, the technical infrastructure, the whole state process and civil engineering, and organization and financial model. So there is all this list of people that you can contact and get in touch with if you're interested in working in this nice project. So about the physics, there is certainly the physics program, people will tell you what you really want to achieve, but there is also, the detector concept. You want really to think about what are the detectors that you want to achieve, you want to build. There is a physics performance. You want to really understand, what are the characteristics of the detector if you want to do this or this measurement. And then clearly, you need to develop some software and computing to simulate and whatever, to analyze all this data. There is EPOL, so energy and polarization, energy calibration and polarization. And then there is all this aspect of the machine detector interface. These are the different people, again, that in the physics side that you can contact if you want to get involved. So now let me give you an overview maybe of the physics that will be done in this machine. So you can understand actually the physics of FCC-ee simply by looking at the evolution of the luminosity as a function of the center of mass energy. And that's really the characteristic of this circular machine, is that the energy, that the luminosity is actually very high at low energy. At the Z pole, for instance, you have a luminosity which will allow you to collect like 100 inverse autobahn in only a couple of years. So just to give you perspective, all the data that have been accumulated at LEP, in particular at LEP1, will be reproduced in every minute, basically. In every minute of operation at FCC-ee, you will repeat all what was achieved in 10 years or 15 years of LEP. Right? And certainly, part of it is because the tunnel is larger, so certainly you have more luminosity, but it's also because, you make tremendous progress in the acceleration techniques, right? Focusing the magnet will be better, etc. So there is basically four or five order of magnitude improvement, basically in the efficiencies of all these accelerating techniques. And then what is really fascinating is that you will have an exciting and diverse program with different priorities every year. It's not that you will do X physics for 20 years. No, you will do X physics for a couple of years. You will do Z physics and electric physics for, again, a couple of years. Then you will do dye boson physics for another year. You will do flavor physics, etc. So really, there is a lot of different and diverse physics that you will do basically 10 or 15 years of operation of this machine. In which order, you will operate this machine is still under debate. There are people that will like to go to the X, to produce the X first, and then study maybe the Z or whatever. It's not totally clear. Maybe there will be some optimization that will still be needed. And I think it will be important actually to remain flexible. I mean, to go back and forth at different energies. And that certainly also puts some, constraint actually on radio frequency cavities that you want to use, because you don't want to change the cavities every month. So you want to make sure that the accelerating cavities are good enough to run at different energies, right, without changing the design of the machines. So again, to give you some numbers, so you will run, for instance, at 240 GeV where you produce the Higgs with the maximal cross section. You will run for something like 3 years, and you will produce about 1.5 million of the Z of the Higgs boson in association with the Z. But you will also produce the Higgs in W fusion, which give you additional information. And as I say, I mean, really what is remarkable for this circular collider is the ability, to run at the Z pole with very high luminosity, and you will be producing close to 10 to the 13 Z boson. So 6 or 7 order of magnitude more than what you did at lab. And we will be discussing actually what you can do with all these Z boson. So you will also be running at 160 GeV, where you produce 2 Ws. And finally, the last stage is when you want to run at 360 GeV to produce pairs of top quark. And we will see what you can achieve actually with this run at TT bar threshold. And here again, you will produce a top quark, but you will also produce additional Z boson. And this additional Z boson will carry additional information that really complement the information that you can collect at 240 GeV. So in each detector, you will be producing something like 10 to the 5 Z boson every second, 10 to the 4 W every hour, about 1,500 Higgs boson per day, and about the same number of top quark per day also. So at the end of the day, as I mentioned, you will reach 10 to the 12 or 10 to the 13 Z boson. So you will get statistical uncertainty of the order of 10 to the minus 6. But that's the statistical uncertainty. If you really want to manage all this data, there is a lot of things, a lot of challenges that you have to cope with. Right? Certainly you need to take care of Monte Carlo generators to simulate those data. You need to develop some software and computing, so detector requirement, detector concept, control analysis, lattice simulation, theoretical calculation, polarization and monocomputation, machine detector interface. That's all topics that are very challenging. Maybe they're not challenging if you have a statistical uncertainty of the order of 10 to minus 3, but if you want to go to 10 to minus 6, it's really the frontier of what can be done at the moment, and people have to be smarter and to work hard really to do all of this. So graphically, what is really the physics program, right? So as I say, it will be articulated around 3 main points. I mean, the X, because at the end of the day, it's solved really as an X factory. So you certainly want to achieve higher precision of the X measurement. I mean, we talk about X factories. The LHE is already an X factory. It's produced. I mean, so far, about 8 million of X has been produced at the LHE. But the problem of LHE is that it's a hadronic machine, so you need, to throw away a lot of data in order to extract the signal out of the background, right? So at the end of the day, you can use about 1,000 of Higgs boson out of the million that have been produced. So here at FCC-ee, every Higgs boson that are produced, you can really exploit and reconstruct them. So this means that basically you have a 3 order of magnitude improvement compared to LHE for what concerns Higgs physics. So this will be useful certainly to determine, the basic property of the Higgs, that mass, the width, or the coupling, in particular the self-coupling. But there is much more that you can use the Higgs for, to extract information about, new physics that are expected to modify the Higgs coupling. So that's one point, the Higgs physics. Then there is a top. I mean, as I say, you will reach the 365 GeV. So that may be the main difference at the moment with the Chinese machine. The Chinese machine is not planned yet. I mean, maybe it will change, but at the moment it's not planned to operate at 365 GeV. It will stop at 240 GeV. So that's really a main advantages at the moment of FCC-ee to run at this higher energy. And again, I will give you some examples. There is actually complementarity between those two run to extract information about the Higgs. It's not enough to run at 240 GeV, because if you are running only at 240 GeV, there are some degeneracies, in the Higgs coupling that cannot be resolved. While if you get the information at higher energy, then you can really break this flat direction in the fit of the Higgs couplings. And then finally, there is this intensity frontier, when you will run at low energy, when you will accumulate very high statistics, right? And what can you do with this 10 to the 13 Z boson? So first of all, you will certainly achieve fantastic electric and QCD measurement, basically repeat all the lab program with improvement by 3 orders of magnitude, in terms of precision. So you can measure all the fundamental parameters of the standard model, the mass of the Z, the width of the Z, the number of neutrinos, N effective, etc., that can be useful also for cosmology later on. But you can also do some QCD measurement, determination of alpha S at MZ with a per mil accuracy. You will understand the quark and gluon fragmentation function, and you will get a clean, non-perturbative QCD information, about the formation of the bound state, etc. That is a little bit missing at a machine like like LHE, but here you have a clean machine that can do that. Finally, you have so many Z boson that you can be sensitive basically to very rare and exotic decays of the Z boson that will be used to do some direct searches of light new physics that are coupled to the Z. So that could be axion-like particle or dark photon. It could be heavy neutral lepton, these right-handed neutrinos, for instance, that could explain the mass of the active neutrinos. It could be long-lived particles, that are expected again in those cosmological approach to the hierarchy problem like axion and things like that, right? So I think that's really the machine that you want to have if you want to understand this new physics model with light and weakly coupled degrees of freedom. Finally, and that's also quite unique to FCC-ee, which is a flavor factory aspect. You will produce 10 to the 13 Z boson, and out of them, they will decay into bottom quark or charm quark or in tau leptons, in such a way that you will actually obtain a lot of heavy meson or taus, right? And the numbers, the statistic is actually enormous. It's much larger than what will be achieved in any flavor factories. And from there, you can maybe hope to have information at the end of the day about the flavor origin of the standard model. But certainly you can achieve fantastic measurement, about, for instance, tau-based electric precision measurement or lepton universality violation test in the tau sectors. And then in B physics, you have the CK matrix element measurement, CP violation in neutral B mesons or flavor anomalies, for instance, in B goes to S tau tau, things like that. Again, you will reach higher accuracy compared to any other machines. So that's what you can do in principle, just by looking at the statistic. Now, certainly, if you want to achieve all this measurement, you need the right detectors. For instance, here, if you want to look at this light and weakly coupled degrees of freedom, you need some a good detector hermeticity, some good tracking and calorimetry. If you want to do B physics, you need some good vertex and hadron identification, right? Some good tagging, energy resolution. So this is really what is going on at the moment, is really to quantify the requirement on the detector in order to achieve this physics program. And yeah, these are examples, for instance, of the characteristics that are needed in the track momentum reconstruction, in the track impact parameter, in electromagnetic energies, etc., etc. So these are the main baseline program of FCC-ee, these 4 different runs at the Z pole, WW, ZH, and TT bar threshold, right? And to achieve basically this kind of measurement. But there is also other opportunities. For instance, you might want to run at 125 GeV. So why 125? Well, because this is exactly the energy of the Higgs boson, right? This is the mass of the Higgs boson. So this is, the energy at which you hope to produce the Higgs boson as S-channel resonance. E plus, E minus going to Z, going to X as S-channel resonance. And this will give you, a unique access to the electron Yukawa. So that's the only place, basically, the only machine can give you information about the electron Yukawa. And if you put the numbers, you have actually enough statistic to be sensitive to the standard model value of the electron Yukawa, provided that you have a dedicated run, for a couple of years at 125 GeV. You could also run at 217 GeV. So 217 GeV is basically the threshold, of the ZH production channel. So usually, you run at 240 because this is the peak of the cross section. But there is also valuable information, just at the beginning, just when you reach the threshold of this process, because then you can learn some valuable information, for instance, X mass. Close to threshold, you are always learning about the characteristic of the mass. There is also the option of running at energy lower than 90 GeV, to really do some QCD precision studies, for instance, running at 20, 30, or 40 GeV, where you will be measuring some fragmentation function on things like that. But there is also opportunities, to exploit FCC facilities differently. For instance, you can use the electron from the injector for bump experiment. You can extract the electron beam from the booster, or you can reuse the synchrotron radiation photon. So for instance, FCC-ee could be the brightest light source ever, right? So these are the things that certainly serve a different community, but that's something that could be interesting also for physics beyond particle physics. Yeah. Okay, these are just some example, a quick, very quick example of what you can achieve directly, in the search for new physics. So, for instance, the way you want to search for axion-like particle is in association production with the photon or with the Higgs boson, and this way, you can be sensitive to the various axion coupling that will be difficult to constrain, at least in the mass range, above 1 MeV or 1 GeV, where basically the astrophysics or beam dump constraints are fading away. And here you can really see the region of parameter space that will be covered by FCC. So it's really complementary to all the constraints. So astro and cosmology are very good to constrain long-lived particles, long-lived ALPS, so with mass smaller than 1 MeV, but really Collider has the best probe for ALPS that are heavier than 1 MeV. For the right-handed neutrinos, again, you can look at them from the decays of the Z boson, through the mixing between the right-handed neutrinos and the left-handed neutrinos. And here you can basically conclude that having 10 to the 13 Z boson can really cover some region of parameter space that are left unconstrained at all from the previous experiment. And what is really interesting is actually that you will basically constrain all the regions that are expected, from the seesaw mechanism. If you expect that these right-handed neutrinos have anything to do, for generating the mass of the neutrino, you have to be above this line, and basically this is a region that will be really probed by FCC-ee. Again, there is some dedicated searches. Here, you need to be sensitive, for instance, of long-lived decays of these right-handed neutrinos. So this is this region here compared to the prompt decays of the neutrino that give you a limit which is around there. So it's really, again, the fact that you need the right detectors to be able to achieve those searches. But with the right detectors, you can really cover basically the entire region of phase space. So let me quickly discuss about the X and electric physics that you can achieve. So again, this is a plot, of the cross section of the associated production of the X with the Z. So there is a peak around 240 GeV. So that's why you want to run this X factory at this energy to collect as many X as possible. So it's about 1.5 million of X boson. And in addition, you have also about 50,000 of X that are produced by W fusion. And then there is also this new energy run at 360 GeV, so at the TT bar run, basically TT bar energy. So the number of X are certainly smaller, because the cross section is decreasing. So there are only 300,000 X that are produced in this way, but the information is actually complementary in such a way that you can actually see that the improvement coming from running at two different energies. So if you look, for instance, at the determination of the X self-coupling, that's something that you cannot determine if you run at a single energy, because the way you want to probe the X self-coupling is basically via quantum correction to the ZH production cross-section. So here, for instance, you have a loop of the Higgs boson, and this loop of Higgs boson will be sensitive to the Higgs self-interaction. But if you have a single energy, there is a degeneracy. You cannot distinguish a quantum correction associated to the X-F coupling from a modified interaction of the X with the Z boson. So a single energy, you have degeneracy and you cannot resolve them. But certainly if you run at two different energy, these two different contributions have a different dependence with the energy, and then you can disentangling them. So that's why you have infinite improvement precision in the determination of the X-F coupling if you run at two different energies. So that's one example, but also the determination of the coupling of the X to the W or the Z will improve by a factor 3 if you add this 300,000 event compared to the 1.5 or 2 million of X bosons that are produced at 240 GeV. There is more quantitative plot in the backup if you want to go there. That's really quantifies this improvement by running at two different energies. Go back here. Doesn't work as expected, sorry. Yeah. So what is really the plan for X physics at the LHC? First of all, it gives you an absolute normalization of the coupling. You have to remember that at LHC, you are sensitive basically to the production cross-section times the branching ratio. So there is a degeneracy. You can always modify the width and rescale accordingly all the X coupling, and you don't. It doesn't affect the product of cross-section time branching ratio. So this means that at LHC you cannot determine absolutely the value of all the X coupling. It's only a ratio that are determined. While at a E plus E minus collider, using the Z recall from you don't need basically to see the X decaying to really have access to the X coupling. So this gives you an absolute normalization of the couplings. You have a measurement of the width. For instance, here you will reach a sensitivity of the order of 1% in the determination of the X, and the mass of the X, will be determined with an accuracy of the order of the width itself, about 3 MeV. So it's one order of magnitude improvement compared to what you can hope to achieve at the end of ILUMI LHC. So there is a model-independent coupling determination and improvement up to factor 10 compared to LHC. So these are the numbers, the accuracy that is expected at the end of high luminosity LHC, and basically what you will achieve with FCC-ee with 4 interaction points. So you will go basically to the per mil level in the determination of the coupling of the X to the Z boson. So this gives you actually an indirect sensitivity to new physics up to an energy scale of the order of 70 or 100 TeV, simply by looking at the deviation of the X coupling induced by new physics, the scale like V squared divided by F, and that corresponds to a mass scale for the resonances of the coupling, the typical coupling of new physics times the value of F. So if new physics is maximally coupled, 4 pi, you will reach 100 TeV with an accuracy of the order of order per mil. And as I say, it gives you also a unique access to the electron Yukawa couplings. 10 minutes, perfect. Yeah, so let me briefly discuss about this, the determination of the electron Yukawa. So the idea is really to look at the X production as a S-channel resonance, right, like this. If you put the numbers, the cross-section is of the order of 1 femtobarn. But of course, this is a theoretical cross-section. You have to take into account actually some energy spread of the beam, some initial state radiation, etc., that reduce basically this cross-section by 1 order of magnitude. So at the end of the day, the thing that you can really observe in your detector is of the order of 200 or 300 attobarn. So clearly, if you run, for 1 year or so, you can have access to these couplings. But for that, it's really important to control with very high accuracy the energy of the electron and positron, so the energy of the beam. And that's why there is this monochromatization idea. So, there is some fluctuation, but you want to correlate basically the energy fluctuation of the electron with the energy fluctuation of the positron in such a way that the two of them compensate, and you're always at basically the same energy in the center of mass. So this is what is called monochromatization. This is something which is not easy. This is being studied at the moment, and there have been some good progress that are being made by accelerator people, right? Of course, it's not enough really to produce the Z and use the Higgs boson. You need to reconstruct the X in your detector, and you need in particular to be able to distinguish the Z from the Higgs boson. And for that, the best channel is actually the decays of the X into two gluons, because certainly you cannot produce a gluon from the Z, and that gives you the cleanest reconstruction channel of the Higgs boson. So that's what people are really studying at the moment, and that's basically the sensitivity that you will reach, according to the luminosity that you can accumulate. And basically, yes, if you have 4 interaction points, and you run for 3 years, basically you will reach at least 3 sigma determination of the electron recovery. It's certainly a challenging measurement to be done, but again, it's really a unique opportunity to have access to these couplings. So now you can ask yourself, well, I mean, do we need FCC-ee actually if I am interested in the Higgs boson, right? Because I'm producing already 1 million of Higgs at FCC-ee, I can study, its coupling to the per mil level precision. So what will be the use of FCC-ee? Well, FCC-ee will produce actually more than 1 billion of Higgs boson. Again, it's hadronic machine, so certainly you are not able to reconstruct all these Higgs boson. Nonetheless, it gives you a unique access, to very rare decays of the Higgs boson, so exotic decays. So simply, you need statistics to have access to branching ratio of the order of 10 to minus 7, 10 to minus 8. You need at least, 10 to the 8 or 10 to the 9 Higgs boson to actually measure, be sensitive to these decays. And the other thing is also that actually, you will have access to a very rich kinematic distribution of the Higgs boson. So for instance, you will still produce more than 1 million of Higgs boson with the PT of the Higgs, which is larger than 1 TeV. So clearly you will reach, region of statistics with very clean signal of a background ratio that, is unique to FCC-ee. So there is really a complementarity between the two programs, EE and HH, for what concerns Higgs. And then there is all this electric precision measurement, that's really a comparison of what was known about the electric oblique parameters at LEP and at the end of high luminosity LHC. And this tiny region is actually what will be known at the end of FCC-ee. So certainly a big improvement compared to what we know at the moment. And as you know, you can use this electric precision measurement to really probe new physics. So again, if you put the numbers, it will give you an indirect probe to a scale of new physics of the order of 70 or 100 TeV. But this is a physics that has to be connected with the electroweak and Higgs sectors. The thing is that even if there is no direct coupling of new physics, to the electric sector, of course, you live in a quantum mechanical world, so everything is mixed together when you take into account radiative correction. So this is, for instance, an exercise that has been done. People have tried to understand all possible UV completion of the Standard Model in terms of one particle. You add one particle that could have a direct coupling to the Standard Model. So again, many of those parameters don't couple at all to the W, the Z, or the X. They couple to, to QCD. And it's only via radiative correction that, this new particle will influence the electric precision measure. So basically, you want to understand, to which extent you are sensitive to the existence of this new particle via this radiative correction. So this is an exercise that was done. They looked at all possible one particle extension of the Standard Model and try to see the radiative correction and how the influence basically this electric sector or electric precision measurement. And this is the result. So this gives you the mass range, the mass reach for all this 48 or 49, basically 50 one particle extension of the Standard Model. And you see that there are some particles, that don't affect electric precision measurement even at the one loop level. So these are, for instance, electric quadruplet. The electric quadruplet, are such that they don't run into electric precision data. But all the other particles basically have a mass reach of the order of 10 TeV or 50 TeV, if the coupling, let's say, to the Standard Model degrees of freedom are of order 1. So it just means that, there is basically no way to escape electric precision measurement for any type of new physics. At least new physics that has some coupling to the standard model. So, okay, flavor physics, I don't have time to discuss flavor physics. You can have a look at the numbers. The statistic is really enormous. And it has also some kinematic advantages compared to all flavor factories, because all these heavy mesons are coming from the decays of the Z, so they are heavily boosted compared to flavor factories where these heavy mesons are produced basically at rest. Okay, no time here. So let me go to the conclusion. So a circular X factory like FCC-ee has a rich potential to search directly and indirectly for new physics. It's an essential part of an integrated program to probe the energy frontier. It perfectly fits the need of high energy physics after the LHC. There is guaranteed deliverable and a broad exploration potential. So we have profound questions and we need to create opportunities for answer them, and FCC will for sure contribute, right? And you have to remember that Collider has a most powerful microscope. We have to study nature at the smaller scale and also from the early moment of the universe, a time where, we have no access to with telescope. So they'll keep providing a quantitative understanding, certainly to make progress forward. Okay, thanks.
Thank you for the very questions.
Yes, this one. Yeah.
Yeah, I'm just curious. Sometimes you maybe combine different models to have like a
Yes.
respect the custodial symmetry, right? So I just curious.
Absolutely.
Some analysis along that direction.
You're absolutely right. I mean, this is assuming that there is a single particle, and now, of course, you can combine different particles and get some constellation. For instance, here, if you impose custodial symmetry, there is no contribution to the T parameter. This is, for instance, the case of this electric quadruplet. So these are actually interesting, objects, because you can go to the custodial symmetry, like the Georgi-Mashashek model. Basically, is one example. You reach a custodial symmetry, and then the constraints are weakened. It's true for the T parameter, but it's not the case, for instance, of the S parameter and things like that, where there is basically no symmetry that protects those quantities. So, yes, some of these bounds will be modified, in explicit UV model when there is some correlation, but some other bounds will remain like that.
Maybe yes. So just curious. So for all those programs, we are concentrating on heavy particles in the standard model. I'm also curious to see, is there any other like a supersymmetry, more well-defined parameter mass, for example, for us to explore and
yes, I mean, okay. For supersymmetry, so there are some studies, of course, of using, electric precision measurement like RL, the ratio of the decays of the X into lepton versus normalized to the hadronic cross-section. So this is useful, for instance, to probe the light electric kinos and things like that, or even some sleptons. So there are some analyses like that. You see really the improvement compared to the high luminosity LHC bounds, right? And then there is certainly the direct searches also at FCC-ee, and I think I have a plot somewhere here, that give constraint for all the super partners, the bound on the super partners, and you see that you reach energy scale of the order of 20 TeV. I don't know for some squark or some neutralinos, I think. So 20 TeV, means that you are really probing a partonic center of mass energy, which is of the order of 30 or 40 TeV. So even larger than what you can do, for instance, at a muon collider. Sometimes, people say, well, 100 TeV PP collider is equivalent to a 10 TeV muon collider. This is not always the case. I mean, bulk of the event is true, but here, you have a tail of event at very large energy, right? That really allows you to put some bound of the order of 20 TeV on those particles. Something that you cannot do at a 10 TeV muon collider simply because it's above the threshold. So,
thank you.
Certainly, there is a lot of things still to be done. I mean, this is only a glance, putting some benchmark. And I'm sure, if you have your favorite model, it would be good to see what FCC can tell about this model.
Other questions? Maybe I may ask one. I'm just wondering how this next generation colliders can help us understanding or maybe solving these puzzles in cosmology, the dark energy. There is this conflict between this vacuum expectation value of the fundamental fields and
Well,
mirror.
I mean, about dark energy, I'm not sure because, the energy scale is more milli-electron volt. Here, I was referring, let's say, to models that are addressing the hierarchy problem, the mass of the weak scale or the mass of the Higgs. So with this relaxon model, the relaxon involves some light and weakly coupled particles that have something to do with Higgs and Z. And then you can see exactly how this machine can probe this parameter space of the models by looking at the exotic decays of the Z, for instance.
I see.
But
Thank you.
I don't know of anything that are addressing the cosmological constant problem. That's a different energy scale. That probing, the vacuum at much lower energy. And I don't know. I don't know if there is any collider that can do that.
All right. If we don't have
Thanks.
any other questions, let's thank our speaker again.
Thanks.